Oh hey, I didn't see you there. Welcome to the Advanced Placement Physics video with Mr. Ralph Ubell. This time we're doing Newton's second law. Enjoy.
Here's Dr. Vincent Mays in all of his glory in 4 elevators. Elevator 1, Elevator 2, Elevator 3, and Elevator 4. In the first elevator, the velocity is 0 meters per second, and the acceleration is 0 meters per second squared. In the second situation, the velocity is 34 meters per second. The acceleration is 4 meters per second squared. In the third situation, the velocity is 32 meters per second, and the acceleration is negative 4 meters per second squared. And in the final one, the velocity is 100 meters per second, and the acceleration is 0 meters per second squared. In order to find the normal force, let's consider a general case where the acceleration is a. Newton's second law states that the net force, F net, is equal to the mass times the acceleration, which is m times a, and this means that the velocity doesn't matter at all in any of these scenarios, and the net force would also be the sum of two forces acting on the object. And so in our case, it would be F net equals normal force, Fn, plus Fg, the force of gravity. We would then manipulate the variables in order to solve for our normal force. So what would happen is it would be F normal equals F net minus force of gravity, because we would subtract this force of gravity here and put it over to the other side. Now we'll proceed to replace some variables to make this easier, and Fn would remain the same because that's what we're solving for. Fnet would turn into mass times acceleration, ma, minus mass multiplied by the acceleration of gravity, which is a constant, negative 9.81, but we'll use g to keep it easy for now. Now we'll take that equation that we just rearranged to solve for normal force, and we'll put it on this page to use it for each of the elevator situations. Let's proceed by saying that our favorite administrator is about 100 kilograms in mass. So 100 kilograms, and this applies to all of them. And so in our first elevator situation, we would plug in these numbers to solve for the normal force. So Fn equals mass, which is 100, multiplied by the acceleration, which is 0, minus the mass, again, which is 100, multiplied by the gravitational force, and this is negative, so it'd be negative 10. We would use 10 instead of 9.81 to make the numbers easier to work with. So the normal force in this case would simply be minus negative 1000 newtons, and so that would be positive because a negative and a negative makes a positive, so that's 1000 newtons. Okay, so working with the second situation, we would again plug in numbers to solve for the normal force. So the mass remains the same, just like the first situation. So Dr. Mays is 100 kilograms in mass, so that would be 100 multiplied by 4 meters per second squared, which is the acceleration, and minus the mass, 100 kilograms, multiplied by negative 10 meters per second squared, which is the acceleration of gravity on Earth. And so, doing math, we would use arithmetic to get 400 minus negative 1000. So, our normal force for the second elevator problem would be 1,400 newtons. Following the same old rules as the other two elevators, good old Mays here is 100 kilograms in mass, so we would simply do the same thing. Fn equals mass 100 kilograms multiplied by the acceleration. In this case is negative 4 meters per second squared minus the mass 100 kilograms multiplied by negative 9.81, or my bad, negative 10 meters per second squared. So the normal force is equal to negative 400 newtons minus negative 1000 newtons. So the Fn in this case would be 600 newtons, because negative 400 minus negative 1000 would be the same as negative 400 plus 1000. Alright, finally, the last elevator is a lot similar to the first one, because as we've said before in the normal force calculations, the velocity has no effect on what the normal force is. So since elevator number 1 and elevator number 4 have the same acceleration, the 0 meters per second squared, we can assume that the normal force is also 1000 newtons. And just in case though, we're just going to do the math to prove it. So the Fn equals 100 kilograms of Dr. Mays, and the acceleration being 0 meters per second squared minus the mass, 100 kilograms, multiplied by negative 10 meters per second squared. So here we are with Fn equals 0 minus negative 1000, and the normal force ends up to be 1000, like we predicted with the same acceleration here. Good morning, and we hope you enjoyed this video.